Hi there. Let's go over how to solve separable first-order differential equations. Sometimes we're trying to solve what are called exact differential equations, where the derivative is given to us exactly, something like this, for example, dy dx equals x squared plus e to the x. This is really easy. It turns out to just be an integration problem in order to solve this. But not every differential equation is quite that simple. Let's talk about this type, separable differential equations. They're not quite as simple as exact, however, they're not that difficult. A differential equation of this form is called separable. It's called separable because it's in a form that consists of a function of y multiplied by a function of x, and we're able to separate the y's and the x's since they're only stuck together by multiplication. So we separate the y's, we separate the x's, and then again it becomes an integration problem, and we can try to solve for y if it's possible. You may find this summary pretty helpful, but maybe not. We're going to go through 3 examples, and I'm sure you'll get it after that. So let's start with our first example. We're asked to solve this differential equation, dy dx equals x squared over y squared, and then we'll also find the particular solution given this initial condition, but let's focus on the general solution first. So notice what we have here is a separable differential equation. We've got a function of x times a function of y. Of course, it kind of looks like division, but division is just multiplication. So this is a separable differential equation. All we've got to do then is separate the y's and the x's. Let's go ahead and do that. And sorry for my voice, I'm still a little bit sick here, so I sound nasally and crackly. So dy dx equals x squared over y squared. We want to separate the x's and y's, so let's multiply both sides by y squared and multiply both sides by dx. That's going to give us y squared dy on the left equals x squared dx on the right. Now that we've separated the variables, all we have to do is integrate the left and the right. We have dy on the left side, so very nicely we are integrating with respect to y, and that's a pretty simple integral. It's just 1/3 y cubed. We could write a plus c there, but we're not going to. I'll tell you why in a second. On the right side, it's a very similar integral with respect to x, just 1/3 x cubed plus c. Now, we can imagine that we just took the constant from the left side and moved it over to the right side, and so I'm just going to leave it as plus c. If you want to be more particular with how you define your constants, go for it. I'm not going to worry about it. So now we've got an implicit general solution for the differential equation, but there's no reason to stop there. We can keep going forward and solve for y in order to find the explicit general solution. To solve for y, we'll just multiply both sides by 3 and then take the cube root. And so we're going to have that y equals 3 times 1/3 x cubed is just x cubed. 3 times c is 3c, but again, that's just a constant, so I'm going to be kind of sloppy and just call it c. And then we would have taken the cube root of both sides of the equation. And so we have that y is the cube root of x cubed plus c, and that is our general solution. Now we can go ahead and find the particular solution given this initial condition. So we just plug the initial condition into our general solution, giving us that 2, because y of 0 equals 2 equals the cubed root of, we're plugging in 0 for x, so the cube root of 0 cubed plus c. Thus, 2 is equal to the cubed root of c, and then cubing both sides, we have that c must be equal to 8. And so our particular solution, given this initial condition, is that y equals the cubed root of x cubed plus 8. And that, real quick, is how you solve a separable differential equation. And here's a graph showing a handful of the particular solutions to this differential equation. And that's all there is to it. We just have to separate the variables, separate the x's and the y's, and then integrate or anti-differentiate both sides. Let's move on to our second example. We're not going to bother with an initial condition here. Let's just find the general solution. And I encourage you to go ahead and give this a try on your own. All right, let's go through it. Again, it is clearly a separable differential equation. We've got a function of x times a function of y. Let's separate the variables by multiplying both sides by dx and multiply both sides by this function of y. So that's going to give us 2y plus cosine y dy equals 6x squared dx. Now that we've separated the variables, we can anti-differentiate on both sides of the equation. The integral on the left is going to be, well, y becomes y squared, and that's going to get rid of that coefficient of 2. And then cosine of y becomes sine y. Again, I'm going to gather the constants on the right side, so I'm not going to bother with a constant on the left side. Integrating 6x squared, that's going to become 2x cubed, and then plus our constants. And that's it. This is our general solution to this separable differential equation. And we're not going to be able to solve this one explicitly for y, so this is an implicit solution. And here's a quick graph of a few members of this family of solutions to the differential equation. It looks pretty nice. Let's move on to one more example. Give it a try. All right, let's get into it. Again, we can see we've got a function of x times a function of y. This isn't currently written in Leibniz notation. You might want to rewrite it like that. So we could write dy dx, because that's what y prime is. Dy dx equals x squared y. Now, again, we're just going to separate the variables. We'll find our general solution, and then we'll worry about this particular solution. To separate the variables, we'll multiply both sides of the equation by dx, and we'll divide both sides of the equation by y. That's going to give us 1 over y dy equals x squared dx. And now we will anti-differentiate both sides of the equation. So 1 over y dy will become the natural log of the absolute value of y, equals 1/3 x cubed plus c. Now we can go ahead and solve for y so that we get an explicit solution. To solve for y, we will exponentiate both sides of this equation, so I'll put them both in the exponent of e. That will, of course, make the natural log cancel out on the left side, and so we're just left with absolute value of y equals e to the 1/3 x cubed. Now, the plus c in the exponent, we could rewrite that if we wanted to, bring it down by exponent rules as a multiplication times e to the power of a constant. But e to the power of a constant is just a constant, so we could just write this as multiply by some constant c. Now, in order for the absolute value of y to equal this, y has to be this or negative this. So we have that y must equal plus or minus c times e to the 3rd x cubed. But again, we can combine constants because plus or minus just means we have a factor of +1 or -1. Either way, we can just combine that with our factor of c, and again, just say this is some constant, and we're just going to call it c. So our general solution to the differential equation is that y equals some constant c times e to the 3rd x cubed. Now we can go ahead and find the particular solution given our initial condition. The initial condition says if we plug in 0, we should get 3. So we'll have that 3 equals c times e to the 1/3 plug in 0 cubed. And of course, e to the 0 is just 1, and so we have that our constant c must equal 3. So the particular solution is y equals 3e to the third x cubed. And if you're curious, here's a graph of a handful of particular solutions to this separable differential equation. And hopefully these few examples were helpful. That's all there is to solving a separable differential equation of the first order. You just got to separate the variables, which isn't too difficult because the idea is that we've just got a product of functions. Just separate them and then integrate and solve for y if you can. Let me know in the comments if you have any questions.
Rather be out of the way, 'cause I don't wanna hear what the people say. I've heard it before, it's such a bore, I sure couldn't take much more.